Distinguished participants, esteemed scientists and participants, it is my great pleasure to welcome you all to 8th session of the Spatial Symposium series titled Latest Developments on Marine Science, organized by Inter-Islamic Network on Oceanography. Today's webinar focuses on the critical topic of marine minerals balancing between economy and environment. As many of you know, Inter-Islamic Network on Oceanography is dedicated to advancing marine science across the world. Through its efforts in oceanographic research, environmental monitoring, and sustainable resource management, INOC plays a vital role in fostering collaboration among member states to address shared challenges and propose innovative solutions for the global marine environment. Unfortunately, I must share that Dr. Abdülmecit Naderi are unable to join us today due to health reasons. We sent them our best wishes for a quick recovery. On a positive note, today's session will feature insightful contributions from distinguished speakers from Iran and Russia, whose expertise will enrich our discussions on balancing economic and environmental priorities in marine mineral use. Before we begin, I would like to remind all participants that you can send all your questions using this Zoom chat box at any time during the presentations. We will collect all the questions and we will ask them at the end of the presentations during the question and answers session. Now, it is great honor for me to invite our first speaker, Dr. Behrouz ABTAHI, to begin his presentation. But before his presentation, I would like to give you more information about Dr. ABTAHI's academic background. Behrouz ABTAHI is a graduate of the University of Tehran and the Moscow Institute of Oceanography. He is an academic staff of university since 1993 and now has a position of Vice President of Shahid Beheshti University in Tehran. He was director of Iranian National Institute for Oceanography and Atmospheric Science 4 years between 2017 and 2021. He was also head of UNESCO Regional Education and Research Center on Oceanography for West Asia. His field of interest is oceanography, marine ecology, and marine resources sustainable management. He has led and participated in a number of research projects in Iranian marine areas, Persian Gulf, Gulf of Oman, and Caspian Sea. His teaching experiences are in the above-mentioned fields. So we are looking forward to listening to you, Dr. ABTAHI. Floor is yours.
Good morning, good evening, good day. Dear friends, I accept my greetings from Tehran. Thank you very much, dear Chair, Dr. Bulent, for introducing me and for organizing this meeting. My special thanks to my colleagues, Dr. Lahijani, Dr. Naderi, Dr. Cherkashov for his contribution to this meeting. I'm very glad today that we can begin and touch a very important item subject in the field of oceanography and sustainable ocean-based development. Again, it's very glad to we have the support of private sector in this meeting. As you know, one of the sponsors of this session is Jamili Fund and the Jamili and the Festival of young scientists and researchers. That is official, very famous scientific festival organized by non-governmental system. And I think it's a new event in a series of scientific activities under the umbrella of INOC. Also, I have to thank Dr. Shermin Açıkçınar, the president of INOC, for her support to providing this scientific event. So I just wanted to do a brief introduction to the subject of SeaBed mining, and my colleagues, Dr. Lahijani and Dr. Georgi, have very comprehensive lecture and speech regarding this item. I wanted only do a small introduction and stay on some economic and environmental aspect of this matter. Dr. Brand, I share my screen.
Yes, please.
Okay, can you see the presentation? Yeah.
Yes, everything is okay. Thank you.
Dear colleague, as you know, 2021 to 2030 is named the United Nations Decade of Ocean Science for Sustainable Development. Especially after the naming this decade, and even before that, one of the main directions of blue economy or ocean sustainable development sectors was mineral resources exploitment in seas and marine areas in ocean. The directions of blue growth or marine economy in different countries, in different regions are maybe different, maybe some directions, 8, 10, more or less directions are the active directions of oceanic economy, but especially 5 sectors are the blue growth sectors determined by European Union. 3 of them are based on the biological resources, and one of them, mineral resources, is focused on non-living resources of the oceans. In the INOC countries, we have around 10 million kilometers area as exclusive economic zones of member countries, as you see in this graph. The total area of exclusive economic zone in all countries is around 137 million kilometers. It shows the potential possibility of member countries to use their marine and oceanic resources. Of course, the mineral resources are not limited in EEZ, and many of them are in the open ocean. So we today speak about the big resources of oceanic area for sustainable development and for using in countries economy. What are the economic benefits of seabed mining? As you know, the seabed is rich in a variety of minerals, including polymetallic nodules, seabed massive sulfides, cobalt-rich crusts. Malaysian waters, for example, from INOC member countries, are known to contain high concentrations of copper, gold, silver, and rare earth elements, which are essential for modern technologies such as batteries and electronics. Seabed mining offers significant economic opportunities for countries, particularly as global demand for mineral continues to grow. Here I wanted to outline the potential economic benefits associated with seabed mining. The first one is the employment opportunities. Seabed mining can create a variety of jobs in a variety of sectors, including engineering, environmental science, logistics, and marine technology. The creation of such jobs can stimulate local economies and provide livelihood for communities dependent on fisheries and other marine activities in marine areas and in coastal communities. Another one benefit of the seabed mining is support for local industries. Seabed mining development can lead to the growth of supporting industries such as equipment manufacturing, research and development, and environmental monitoring services. Such diversification can strengthen local economies and increase resilience to economic fluctuations. Another use of the sector is technological advances, innovation in mining technologies. The need for efficient method for seabed mining stimulates innovation in technologies. Countries involved in seabed mining are likely to invest in research and development to improve extraction methods, which can have spillover benefits for other sectors such as offshore oil and gas industries. Knowledge transfer is another benefit of the sector. Collaboration with international companies and research institutes can facilitate knowledge transfer on sustainable mining methods and advancing technologies. This can empower local industries and contribute to long-term economic growth. And the collaboration that forming between us, between our institutions or countries, between us and Russian Institute is the example of this kind of benefit of this section. Revenue generation is another part, and government can benefit from seabed mining through licensing fees, royalties, and taxes collected from mining companies. This fund can be reinvested in public infrastructures, education, health, and environmental issues. And the last benefit I can name the strategic resource security. As you know, the land resources are in high stress and high impact of human activities, and by developing domestic seabed mining, countries can reduce their dependence on imported minerals and on land mining industries and activities. So we can see that in this direction of oceanic industries and technologies, we can find many opportunities for our countries and for economies. It was about the importance of the item, but the very important part of the mining in oceanic areas and in seabed is the environmental concerns and risks. They must be noticed in every activity we do in oceanic regions, of course. As you see here, some concerns we have regarding the development of mining in marine areas. The first one is impact on marine life. Research shows that a single noodle mining operation can produce between 30,000 to 80,000 cubic meters of sediment daily. The equivalent of filling thousands of dump trucks. These sediments can create long-term stress on marine organisms, especially if disturbance occur frequently. The second environmental impact caused by marine mining is making sediments plumps and disturbing water quality. Mining creates significant sediment plumps that can impact water quality over large areas. These plumps are composed of fine particles that can suffocate marine life by clogging the feeding structures of filter feeder such as corals and sponges such as zooplankton and other marine living resources. Sediments can also disrupt visual communication between species and alter the physical and chemical properties of seawater, including oxygen level, pH, and temperature. Another negative impact of marine mining is direct harm to marine organisms. The physical presence of mining equipment poses a direct threat to marine life. Less mobile organisms and particularly vulnerable to being killed or injured by heavy machinery operating system on the seafloor. Additionally, warm wastewater from mining operations can further threaten marine life by introducing heat and toxic substances into their environment. Another one negative impact is long-term ecosystem disruption. The combined effect of habitat destruction, sediment plumps, and direct harm to marine organisms can result in long-term disruption to deep-sea ecosystems. Many deep-sea species are rare and have evolved over millions of years. Therefore, their extinction due to habitat removal can lead to irreversible change in biodiversity in deep ocean and in marine ecosystem. Habitat destruction is another possible impact of marine mining. One of the most immediate and serious impact of seabed mining is habitat destruction. Mining operations often involve the removal of hard substances that serve as critical habitat for variety of marine organisms, including sponges, corals, and other sessile species. Destruction of these habitats can lead to permanent loss of biodiversity, as many deep sea species are slow to reproduce and may not recover from such disturbances. Ecosystem restoration, the recovery time for damaged ecosystems can be decades to centuries. So it is critical to assess the long-term impact of mining activities before commercial exploitation begins. As you know, one of the important threats in the modern ecological situation in oceans is noise pollution produced by different techniques, by shipping, by oil platforms. Seafloor mining also can create noise and light pollution that can disrupt the natural behavior of marine life. Species such as whales and other large marine animals use sound to communicate and navigate. Increased noise level from mining activities can interfere with these important functions. So, the last negative impact I wanted to emphasize that the potential impact on fisheries and food security. Because of the above-mentioned impact on ecosystem that directly can impact on fish stocks and resources. So I finished my presentation, and Dr. Ben, can you see me?
Yeah.
Yes. Yes. So I tried to do a small introduction to the subject and say about our concern everywhere and every time when we speak about the using of marine living or non-living resources. It's an environmental aspect of each and every activity that we do in marine and oceanic areas. But again, I want to say that the exploitation and using the marine mineral resources is new direction and new economic possibility for our countries, and we have to begin and have to study deeply this subject and this issue for developing of science and developing of economy of our countries. Thank you very much for your attention, and thank you, Dr. Bonnet.
Thank you very much for your presentation, Behrouz. May I ask you to stop sharing your screen? There is a button, stop share. Can you? Yes. Thank you very much once again for your very nice presentation. I think we will ask you questions at the end of all presentation. I would like to invite the second speaker. He is Hamid Alizadeh Ketek Lahiyani. Before his presentation, I will also give you information about his academic background. Dr. Lahiyani is a professor and tenured faculty member of Iranian National Institute for Oceanography and Atmospheric Science since 1998. He was research deputy at this institution around 12 years. His field of interest is quaternary climate, marine geology, and marine hazards. He has led and participated in a number of research projects in Iranian peripheral seas and internal lakes. His teaching experiences are in the field of oceanography, marine geology, and non-living characteristics of Iranian seas, and INOAS and State University. So, Dr. Lahiyani, floor is yours. We are really looking forward to listening your presentation.
Hello, everybody. Good morning. Now my presentation is in the screen. No. Can you see my presentation?
Yes, everything is okay. We will listen.
Hello, everybody. I appreciate the organizer of this meeting. My talk is about the perspective of mineral resources in Macron bottom sediments. Macron is part of coastal territory of Iran and Pakistan, and it stretches for around thousands of kilometers from the Strait of Hormuz in the south of Iran to near Karachi in Pakistan. The Macron coast is part of the actionary wedge of the Macron subduction zone formed by subduction of Arabian plate under the Eurasian plate. Macron bottom sediments originate from Macron offshore and Macron onshore and Macron offshore that bring the sediment in the basin from the catchment and from the biological sources and water masses. Macron encompasses onshore and offshore parts. Remnant of the collided margin make up the hanging wall backstop of the onshore accretionary wedge, which includes inner, outer, and coastal Macron. The onshore Macron, with around 200 kilometer width, is limited to Jazmurian and Mashkel depressions in the north and Gulf of Oman in the south. Lithologically, inner and outer Macron consist of around 7 kilometer deep marine turbiditic sandstone and shale intervals, and coastal Macron is dominantly composed of deep and shallow marine and deltaic sandstone and marls. Macron's climate is arid, semi-arid. Macron receives precipitation both from westerlies in winter and monsoon in summer. Occasional intensive monsoon precipitation causes flooding, and sediment plumes go deep down in offshore Macron area. And here is the view of the Macron coast. This barren topography makes susceptible for erosion, especially during the intensive monsoon precipitation. It's the Iranian part of Macron, coastal Macron. And it's the another view from the seaside to the rocky shore of the Macron area. It's the view during the extreme cyclone during instrumental measurement that happened in 2007 7 on Makran coast, the high waves hit the Makran Brackish shores in the Iranian Makran zone. But offshore Makran is 10 to 40 kilometers wide, reaching a depth of around 100 meters. Continental slope extended around 70 to 100 kilometers. Upper slope down to 700 meters display evidence of mass wasting with gullies and canyon. Lower slope consists of 7 to 100 meters highest cap, and the easternmost ended to Dadrimpel Trough and Murray Ridge in the border of the Arabian Sea. And in the offshore Makran, several north-south gullies and ridge and troughs are the prominent offshore morphology in the slope. And in the water area, you see the flooding and river plumes that happened in the event of the intensive precipitation in 2005. Here is the that I changed my presentation in the last minute. I should ask Dr. ABTAHI, can I change my the new presentation here? Just it's the old presentation that I shared. Just a few minutes, just a minute. I'm not sure this is the right one. I hope this is okay. This is the water column properties in the Makran area that display the temperature, salinity, and dissolved oxygen. Here in the you see the thermocline bottom line is the around 24 degrees Celsius in the Makran waters, both during the monsoon and monsoon seasons. And in the middle panel, you see the signature of the Persian Gulf waters that shows with higher salinity entering into the Gulf of Oman. And in the right panel, you see the oxygen, dissolved oxygen, but the dissolved oxygen is very low in the Gulf of Oman. In the Makran shelves, that hypoxia or low oxygenated water started from the depths of around 50 meters downward. And it's another transect of the Gulf of Oman in the Makran shelf waters just before and after passing cyclone Shaheen in 2022. Cyclone Shaheen elevated the oxygenation by upwelling and turbulence in the shelf waters, and had significant impact on the waters. Just here also you in the middle panel you see the signature of the Persian Gulf intrusion into the Gulf of Oman. Here the map show the different elemental concentration in the Gulf of Oman that shows two concentration, one in westernmost showing the penetration of the Persian Gulf waters into the Gulf of Oman, and another one is the anticyclonic activity in the central part of the Gulf of Oman. And here is the also concentration of the chlorophyll A and the turbidity in the Gulf of Oman. Also is here we see just in the western part the plume of the Persian Gulf intrusion into the Gulf of Oman, and in the central part impact of two prominent gyre cyclonic and anticyclonic in the Gulf of Oman. Along with the oceanic process in the Gulf of Oman, the Gulf of Oman and Macron area is affected by the process beyond its region. It's the water masses that penetrate into the Gulf of Oman is the Persian Gulf water from the west, the Red Sea water, saline and warm water from the southwest, and the Antarctic circumpolar water and Antarctic bottom water, as well as North Atlantic deep water penetrating in the northwest Indian Ocean. They help bring the material, mainly dissolved metals, into the Arabian Sea and the bottom area of the Gulf of Oman. Here is the schematic diagram of the water stratification in the Macron area. Here you see the Indian Ocean surface water, IOSW, and the intermediate water and deep water. And in partially the Persian Gulf water that located in the middle parts, penetrating in the Gulf of Oman from the Persian Gulf. And as the Persian Gulf has very low residence time, the material dissolved and particulate materials coming from the Taurus and Zagros mountains coming into the Persian Gulf, it transfers to the Gulf of Oman that could elevate some elements in the Gulf of Oman. Here's the our research vessel, Persian Gulf Explorer. We have conducted several expeditions in the Persian Gulf and Gulf of Oman during the past 2 decades, and some result that have I displayed is from the result of this expedition into two basins, and we have deployed different instruments in the Persian Gulf and Gulf of Oman for our research work, including box corer, gravity corer, piston corer, CTD, water sampler, on board of the Persian Gulf Explorer. Bottom sediment of the Macron shelf, or is the archives of the onshore and water column signature. The surface sediments are mostly silty and partially close to the coastal area or sandy sediments, and they show the elevated amount of carbonates in the sediments, and occasionally even in deeper parts they show coarse-grained sediments. And in core samples or core sediments, also muddy sediments dominated, but they occasionally show elevated amount of the coarse-grained sediment even in the slope area. Here is the signature of the different sedimentary properties in the core sediments of that we retrieved from the slope area. Even in the deep slope, we see the coarse grain sediment in the slope area, that they are signature of the mass wasting in the deepest slope of the Macron shelf and slope. And mineralogically, that we studied the sand fraction of the sediment in the Macron shelves. They show different heavy minerals, including ilmenite, tourmaline, rutil, hornblende, and zircon. The concentration varies from 5 to 14% in the shelf sediments. And the muddy sediment of the slope area mainly composed of the clays. That the kaolinite is the main component of the clay minerals in the slope area. Here is the SCM EDS that display carbonate and kaolinite and chlorite in the bottom sediment of the Macron slope. One of the main source of the bottom sediment in the Macron slope is the aeolian input that coming from the around catchment basin, mainly of the desertic. The geochemistry of the shelf sediments in the Persian Gulf that our colleagues studied rare earth element, a few rare earth element in the Persian Gulf. They show the slightly elevated or enriched cerium in the Persian Gulf surface sediment. Again, Persian Gulf sediment are mostly carbonate, and that they are depleted mostly from the rare earth element. And another point is that due to high velocity of the currents in the Persian Gulf, due to tidal currents, density currents, and wind-induced currents, the residence time of the water mass is very low, and many particles transferred into the Gulf of Oman. Here is the 9 rare earth elements that have been measured in the Macron shelf sediments. They show a little more elevated amount in the shelf sediment in the Gulf of Oman compared to the Persian Gulf. And one of the reasons might be the role of the Persian Gulf flux into the Gulf of Oman. Another point is the impact of the water masses that coming from the Northwest Indian Ocean into the Gulf of Oman. And along with the concentration of rare earth elements in the Gulf of Oman that show elevated amount and more potential for future research. Another oceanographic element of the Gulf of Oman is the process that have experienced in the last glacial maximum. I mean, last glacial maximum it's occurred around 20,000 years before present. That the sea level was around 125 meters lower than the current sea level, and the Persian Gulf was desiccated, and all rivers joined in the central part of the Persian Gulf and entered into the western part of the Gulf of Oman, and made a vast delta in this area. and the shelf area of the Gulf of Oman also was desiccated, and there is a relict beach in the border between the current shelf and slope area, and the relict beach is another source for old beach placers based on the current research that they show high elevated amount of the heavy minerals. The relict beach of the Gulf of Oman is another source for the future research and prospecting. Here it shows the rare earth element European in the Arabian Sea. Is the role of the oceanographic process in the Arabian Sea that enhanced the concentration of the rare earth elements in the oxygen minimum zone of the Arabian Sea. It's the Northwest Indian Ocean, including the Makran area, Gulf of Oman, they are one of the prominent area of the oxygen minimum zone. The process that occurs in the oxygen minimum zone release more metals and help to concentration of some elements in the water column as well as in the bottom muddy sediments. My last slide is about the overall view of the Makran shelf. Makran margin, continental margin, including shelf and slope, and continental rise, and the lower part is the abyssal plain in the Gulf of Oman. We have fluvial input from the catchment basin. We have aeolian input surrounding catchment or desertic. And one of the main components of sediment input is the fluvial aeolian. And another source of the sediment in the Gulf of Oman is the turbiditic or mass wasting because of the very sharp slope in the continental margin. The biological import is another source for the enrichment of some elements that going down in the bottom sediments, and the last one is the oceanographic current that coming from the west, from the Persian Gulf into the Gulf of Oman, and from the east, from the ocean conveyor, including Antarctic bottom water, that going deep into the Gulf of Oman. The whole process incorporating the elevation or enhancing the some elements in the bottom sediment that our first reconnaissance show it, and it has the potential for the more research for the rare earth elements in the bottom sediment of the Makran zone, as well as the relict beach that not studied yet. Relict beach in the south water around 125 meters can be enriched by old beach placers that happened during the last glacial in the Makran, currently Makran shelf. Thank you for your attention. Thank you.
Dr. Lahiyani, thank you very much for your very nice and informative presentation on mineral resources in Makran bottom sediments. I believe that this presentation will increase the information of young researchers who are listening to you. So thank you once again. may I ask you to stop sharing your screen?
Yeah, no.
Yeah.
Stop sharing.
Yeah.
Can you stop sharing, Behrouz? Yes. Thank you once again. Before going to the next and final speaker, I would like to remind all participants once again that you can send your questions to all participants and speakers using Zoom chat box. We will collect all of them and ask them at the end of all presentations. So our final speaker is from Russia. He is Georgy Charkashov. Before going to his presentation, I would like to give you more information about his background. He is Deputy Director of the Institute for Geology and Mineral Resources of the Ocean of the Ministry of Natural Resources and Ecology of the Russian Federation. He holds a doctoral degree for research of seafloor massive sulfide deposits of the Mid-Atlantic Ridge. He is chief scientist of 13 ocean-going expeditions for research and prospecting ferromanganese and SMS deposits, including diving missions on MIR and other submersibles. Professor Charkashov is member of the Legal and Technical Commission of the International Seabed Authority and professor of St. Petersburg State University. He served president of International Marine Minerals Society between 2011 and 2012. Professor Charkashov published more than 130 articles and chapters in monographs related to marine geology and deep sea mineral resources. Floor is yours, Charkashov, and I would like to share the screen for his presentation. I think the screen is available for all of the participants.
Yes, thank you very much. Thank you very much, dear hosts. And it is great honor for me and great pleasure to be a lecturer in this workshop. This is new audience for me, and I hope this is not the last time when I give a lecture. And I am waiting for feedback from your colleagues and for future cooperation. And I will tell you today a kind of review about deep sea mineral resources and different characteristics of them, and what we are doing in the deep water, and what kind of development or what kind of results we are looking for. So next slide, please. So the list of the mineral resources in the ocean is not very long. And in the deep sea mineral resources, we have just 3 types of these minerals. This is ferromanganese nodules, ferromanganese crusts, and seafloor massive sulfides. You see, just 3 types of deposits in the ocean, in the deep ocean. And we know in the continent we have tens or hundreds of deposits. But what is the main difference between ocean and continental ores? This is resources. So resources of these types of minerals is huge. And this is a difference between the between onshore and offshore deposits. So I will tell you about some characteristics of these deposits, mineral deposits. You see a list here. I will not read it, but we will follow this plan. Next slide, please. So this slide shows us the geological setting and water depths of the different types of deposits. And you see that from the shelf areas we have, from the shallow areas we if we will go from the right to the left, first we will see that we have aggregates. This is very important type of the shallow water mineral resources, and we use it for construction works and for the sand and gravel. For many industries is very important part, very important type of the mineral resources. Then we go to the placers, and the previous speaker told us that there are some perspectives, some prognosis for Persian Gulf regarding these placers. This is one of the major source for many minerals such as diamonds or tin or gold for the industry, for the world economics. Then we have phosphorites. This is also not deep water resources, but also it is intermediate between the shelf areas and the deep areas. The water depth for phosphorites is around 400-500 meters. And you know that phosphorites, this is a major source for the agriculture, we use it in order to all of our vegetables and fruits grows good in a good way. And so all fertilizers we can get from these phosphorites. Then we go further to the deeper, and we will find the oil and gas. Of course, this is not the topic of my lecture today. And then we are coming to the deep water, for the deep ocean. And as I mentioned, there are three types of the mineral resources. This is nodules, crusts, and sulfides. So manganese nodules, ferromanganese nodules, this is the deepest type of the mineral deposits. The water depths for nodules are around 4 and 5 kilometers. You see, this is a very deep type of the formations. Then we are coming to the ferromanganese crust, and they are related to the seamounts. They are sitting on the slope of seamounts. And finally, to the left, we go to the polymetallic sulfides, which are related to the mid-ocean ridges and island arcs. And you see in the bottom of the slides, we see the water depths for these three types of the minerals. Nodules is the deepest, 4 kilometers. Crust is the shallowest inside of within this list, and sulfides is between the deepest and the shallowest. Next slide, please. And here we can see the Atlantic Ocean, and once again you see three types of these deep sea minerals and their geological setting. So nodules are related to abyssal basins, crust for the seamounts, and sulfides for the system of mid-ocean ridges and island arc systems. Next slide, please. So it is very important aspect for our deep sea minerals. This is a legal status. You know that the whole ocean, there are two parts of our ocean. This is the so-called area. This is international area. This part of the ocean belongs to all humankind, and for nobody and for everybody. And also there is an exclusive economic zone and extended continental shelf. And you see here that in the right part of this table, the distribution of this area and distribution of the, okay, go back, please. No, go back. Yes, thank you. And so half and the half. So the continental shelf, legal continental shelf, and area is relatively equal for the distribution. And for different types of deep sea minerals, we have different amount of these minerals within the area and within the continental shelf. So please come to the next slide. And here you see this map, which demonstrates the distribution of exclusive economic zones around the continents. All coastal states have this area called exclusive economic zone. This is the jurisdiction of this country. This is national jurisdiction. But beyond this exclusive economic zone, we have so-called international area. And most of the deep sea minerals, they are sitting in this area, international area. Look for the next slide, please. This is a distribution of the ferromanganese nodules. And you see that most of them, they are sitting in the area. So they belong to the all humankind, mankind. And especially this area in the Pacific Ocean, so-called Clarion-Clipperton zone, between two fracture zones, Clarion and Clipperton. This is huge area, and this is favorable area for the nodules. And it is sitting, the whole of this Clarion-Clipperton zone is within the area. And exactly here, particularly here, all contractors who applied for the future exploration and exploitation, their areas, this is exploration areas, they are situating in this Clarion-Clipperton. But sometimes nodules could be distributed within the economic zone. This is the case of many island countries in Pacific when we have the situation where within the exclusive economic zone, we have a lot of ferromanganese nodules. Next slide, please. The second type is ferromanganese crusts, which I told you that they are related to the seamounts. They are also mostly they are distributing in the area, but sometimes they also they distributed within the exclusive economic zone. And you see why I am talking about this. This is two different law or legal regime. For the exclusive economic zone, this is national jurisdiction. For the area, this is international jurisdiction, and International Seabed Authority dealing with these deep sea minerals, which are related to the beyond the exclusive economic zone. Next slide, please. And the last, this is about the polymetallic sulfides. You see that light blue, this is economic zones, and part or half of the sulfides, they are distributing within these economic zones, and another half is out of exclusive economic zone within the area. Next slide, please. And this is a slide to show us the areas where the activity is the most intensive. Next slide, please. So one of example is Norway. Look here. This is the map which demonstrates us the exclusive economic zone of Norway and extended continental shelf of this country. And as a result of this extension of the continental shelf, they got the right to operate, to explore and exploit not only their exclusive economic zone, but also extended continental shelf. And as a result of this extension, they got the part of the mid-ocean ridges. This is Mons Ridge and Knipovich Ridge, where a lot of deep sea polymetallic sulfides are occurred. and also polymetallic crust, ferromanganese crust. So this is results of some efforts of this country, and now within their area, within their national area, they have a lot of the minerals, deep sea minerals, and they have very ambitious plans for how to develop them, starting from exploration and further to exploitation of the crust and sulfides. Next, please. And another characteristic, this is a distribution area of the different types of deposits. You see the largest distribution area is for nodules, because nodules, they cover the huge areas of the seafloor. They are sitting on the surface sediments like potatoes on the surface, and you see this is thousands and tens of thousands square kilometers which they cover. The crust, this is a more local type of deposits, and the sulfides, they cover just very small areas within the ocean. Next slide, please. And here you can see the comparison of the exploration area for one contract. Contract means exploration contract. This is a place where you can make your exploration study. And you see here that manganese nodules has the very large exploration area compared with the crust and sulfides. Next slide. And now some characteristics of each type of deposits. So nodules and crust, we call them 2D deposits. When we are saying about morphology, this is 2D deposit, two dimensions. So they are sitting on the surface of the seafloor, and for nodules, this is just 5-10 centimeters on the seafloor, and the crust, this is also up to 10 centimeters. They are sitting immediately on the seafloor. But the sulfides, this is 3D deposits, and they have the thickness, and this thickness not centimeters, but this is meters, tens of meters, up to 100 meters. And you see here also how they look like. The nodules, this is, as I told you, this is like potatoes on the seafloor. The crust, they cover the slopes of the seamounts. They look like here. And the last picture in the right, below, you see the structure of the typical seafloor deposits. Next slide, please. And if we are talking about mineralogy, nodules and crust, they have a very similar mineralogical composition. The major minerals are oxides and hydroxides, opposite to sulfides. Sulfides, this is minerals, and following their mineralogical composition, we have the list of these metals which enrich the nodules, crust, and sulfides. So this set of metals for nodules and crust is rather similar, but crust is rather enriched in cobalt, twice higher than in nodules, and very high concentration of rare earth elements, which are very important for the modern industry and modern economics. And very many minor elements, and rare elements, which are very also important. And this is secondary. They have a secondary importance, but also they are, when we are talking about what we can get from the deep sea minerals, we should mention that minor and rare elements also enrich all of these types of deposits. And the last line is very important. This is great distribution. For crusts and nodules, this is very simple and very good for exploration and for future exploitation, because they are rather homogeneous on a regional scale. You can get a sample from Indian Ocean and in Pacific Ocean or in Atlantic Ocean, and you will get approximately similar composition and similar concentration of the elements and metals in the nodules and crusts. And opposite for the sulfides, they are very heterogeneous, and this is a very important issue and the problem for the future development of this type of minerals. Next slide, please. And here you can see the potential value of different metals in different types of deep sea deposits. You see for the nodules and crusts, this is four major metals. This is manganese, cobalt, nickel, and copper. And for sulfides, this is copper, gold, zinc, and silver. Next slide. And other characteristics, I will not go too deep to this issue, but maybe for formation process, I will tell that the generation and formation of nodules, crusts, and massive sulfides, they're different. For nodules and crusts, this is so-called hydrogenetic mechanism. So the metals coming to these deposits immediately from the seawater, sometimes from the sediments, like in diagenetic nodules, but this is mostly from the seawater, from the normal seawater, and they grow a very long time. This is 1,000 and millions of years. Opposite to massive sulfides, the formation process is so-called hydrothermal. They are generating from the hot vents, or maybe you heard the black smoker phenomena, which was discovered 40 years ago in Pacific Ocean. And the age is comparable with the nodules and crusts, is very low. The oldest seafloor massive sulfides, the age of them is 100,000 years. As for the ancient analogs, we have a very good ancient analog for massive sulfides. This is volcanogenic massive sulfides. This is a very important source for the metals deposits which we have on the continents. And we mine this deposit during, I think, 200 years at least, and a lot of copper and zinc and lead we are getting from these volcanogenic massive sulfides. But the interesting point that we have no analogs in the geological records for the nodules and crusts. There are some explanations for this, but it takes another 10 minutes to tell you about this. Next slide, please. And if we are talking, this slide show you this idea about this modern and ancient sulfides. This is a line demonstrate us the geological history of our planet. And during the whole history of our planet, this volcanogenic massive sulfides generated. And we see now, this is a zero in the right side of this line. This is the time of this is our time. And when during this time, these seafloor massive sulfides are generating. So during this 100, say, or 200,000 years, not a lot of these massive sulfides were generated, comparable with the more ancient ages during the Earth history. Next slide, please. And other characteristics, for example, so footprint, if you will start to mine, what the area will be disturbed on the seafloor. And you see this is a major, or the biggest area for nodules. This is around 150 square kilometers. For crusts, this is tens of kilometers, but for massive sulfides, with this very small areas will be disturbed. So the footprint is the lowest for the massive sulfide. So you see, I am trying to show you, to tell you that different types of deposits, they have advantages and disadvantages. And this is a good example of this. So if we are talking about processing, so when we will mine the ore, we should process it. We should extract the metals. And you see here that for mesosulfides, because we use for volcanogenic mesosulfides for the long time, so we have already this technology how to extract the metals. But for nodules and crust, it should be new one. And some specific problems, I will not go deeper. Next slide, please. This is footprint, which I mentioned, and the largest footprint will be for the nodules, the less for the crust, and the smallest one for the seafloor massive sulfides. Next slide, please. And I mentioned regarding processing, this is a very complicated slide which demonstrates the technology of extraction of the metals. And as I told you, it is already designed, it is already existing, and we can, if we will get this ore, we can start to process it. Next slide. And I mentioned there are some issues. This is an example of this issue. So, for example, this SMS, they have some corrosive features. And you see this example when this corrosive, they impact on our boxes. And if we have this small size effect, you can imagine when we will get hundreds and 1,000 tons of this, it should be environmentally not so friendly. Next slide, please. And global resources. Now we are talking, I started from this and I told you that nodules, crusts, and sulfides, they differ from terrestrial, from continental deposits on their resources. And you see here the billions of tons which we have globally, and we have in the prime zones and within the exploration areas where the companies and countries are planning to start mining in future. Next slide. And now about some metal resources and their comparison between the terrestrial and seabed. You see in the left, this is a cobalt, nickel, manganese, and molybdenum, which is much higher resources we have in the ocean comparable with the land. You see that it is almost 30 times higher resources of cobalt in the ocean than on land. And for all of these four metals, cobalt, nickel, manganese, and molybdenum, we have higher resources in the sea than in on the land. And on the right side of this slide, you can see silver, copper, and zinc. It is, when we are talking about resources in the ocean, we see here that resources in the ocean is lower than on land. But it is very important input for the future economics of our countries and globally for all countries. And you see the left part of this slide. It is demonstrate that these four minerals, four metals, they are concentrated in nodules and crust. And from the right, this is sulfides. Once again, for the nodules and crust, this is a very important source for these several metals. And from the right side, this is important, but it is addition. This is not the major source for these metals, but it is additional source of metals for the future economy. Next slide, please. And exploration methods, they are similar for all three types of deposits. And the basic methods are, this is bathymetry, this is side scan sonar profiling, photo and video profiling, and sampling, of course. This is, we use it for all three types of minerals. But there are some specific methods which we use only for crusts. For example, we use hydroacoustic profiling. For sulfides, we use hydrophysical. This is CTD measurements, measurements of the different parameters of the seawater, because the anomalies in seawater can give us the information or indication of hydrothermal processes and deposits which should be somewhere nearby our measurement point. And drilling, of course, important for crust because we have some thickness. This is tens of centimeters. No, not tens, but 10 centimeters. But for sulfides, which I mentioned, it is tens of meters. And so in order to get information regarding the thickness and in order to estimate the resources, we should drill it. And also a very important part of the exploration for sulfides are geophysical methods. This is electromagnetic and seismic, which give us information again about the thickness and allow us to estimate the resources of deep sea minerals. And you see here this in the bottom of the slide, the trend that the complexity of the methods each is less for nodules, intermediate for crust, and the most most comprehensive for sulfides. Next slide. And now we are coming to the end, and I told you about exploration, and now for the future exploitation. So usually we are asking, okay, so you have your minerals on the sea bottom, but how you will mine them? And I should say that there are some technological consideration, technological schemes, and already projects which allow us to get these deep sea minerals to recover these minerals from the sea bottom. And generally, this mining system consists of three major parts. This is a seafloor mining tool, which collect these deposits on the seafloor. This is riser or lifting system in order to lift this stuff to the surface, and finally mining support vessel, which are on the top of this system and the surface of the sea. And these three types of minerals, they exploitation or mining technology differ by
Dr. Yorgi, I think we have a communication problem, internet problem with Yorgi. Let's wait 1-2 minutes. Yorgi?
Yes, I'm here.
Okay, thank you.
Sorry, I don't know what's happened, but maybe something between our countries problem. Anyway, so we are coming to the end, and please, next slide. Yes, this is new technological approach for deep sea mining. And for example, on the left side, this is a Russian project, how to collect the nodules using the swarm of these drones. Each of these guys, they will collect the nodules by these hands using the artificial intellect, and they will have computer visual, and they collect only nodules, not touching the animals. Okay, so this is for a moment, this is only the idea, but they are trying to make it true. The second project is about vertical mode of SMS mining, not using the crawlers, not tractors, which are moving along the seafloor, but using the system to mine the seafloor massive sulfide from the seawater. So it is more environmentally friendly. And the last picture about the collection of the crusts. They are cutting the crust by also the cluster of these mechanisms, of these machines, and they collect the nodules, not nodules, but crust, and send them to the container up to the surface of the sea. Next slide, please. Okay, and we had a very nice presentation, the first presentation regarding the environmental issues. I will not go to this issue, but generally we are when we are talking about future deep sea mining, of course, we are talking about the balance between the economical issues, between technology and environmental. And this is very, very, very important, part of our business for deep sea mining, because we should do all of this operation very carefully. And all technology which we design or which we consider as a future technology for deep sea mining, they should be maximum environmentally friendly. So this is our very important task. And next slide, please. And finally, when I'm coming to the end, to sum up, I should say that characteristic of these three types of deep sea resources, as well as approaches to their development, are in big variety. I hope that you realize that they are very different to these three types of minerals. Nodules and crusts have very many similar characteristics, while sulfides differ from them considerably. And the last, that the following priority for future mining currently is considered. This is the first priority of this is for nodules, and the next is for crust, and the last for sulfides. And now all contractors, they concentrated their efforts for the nodules, because it seems that it will be the first type of deposits which will be start to exploit, which will be started to be mined. So I guess this is the end of my presentation. Thank you very, very much for your attention.
Dr. Yorki, thank you very much for your excellent presentation on deep sea mineral resources. So we can come to questions and answers session. I think we have one question for Dr. Lahiyani. I think Dr. Lahiyani read the question, or I can read again. Dr. Lahiyani?
Yeah.
The question is, have you conducted isotopic studies to determine the origin of the sediments? Can amounts of rare earth elements present in the sediments be economic? This is the question.
I didn't hear. I didn't hear.
May I repeat again the question? Do you hear me?
Yeah, I hear you. Yeah.
The question is, have you conducted isotopic studies to determine the origin of the sediments? Can amounts of rare earth elements present in the sediments be economic?
Not yet. Not yet. We will conduct a new expedition in the next year in the Gulf of Oman for deep coring by piston corer down to 6 meters deep in sediment, and we'll follow our research on the sediment. Not yet. Not yet.
Okay. I think we have another question. Given your experience and the geological characteristics of the Iranian seas, do you think there is a chance to explore mineral resources in the water belonging to Iran?
You know that if you mean mineral resources in the water, it might be, especially in the Persian Gulf, where the desalination plants working, and the output of the desalination can be used for the mineral resources. Another source is the not water and coastal area. And in coastal area, as experienced in the Soviet period in the Caspian Rim countries, now in Turkmenistan and Republic of Azerbaijan, the fossil waters contains iodine and bromine. And in our coastal province of Golestan province in the southeast Caspian coast, they exploited the iodine from fossil waters. There is the potential in coastal area from fossil waters. There is potential using just the waters, but sediment is too soon. We say that we can use mineral resources from sediments. Some our analysis show elevated amount, but it's not so big to be economic now.
So thank you very much for your answers. I think
Maybe I will add something.
Jorge will, yes, go on, please.
Yes, I guess if you are talking about shallow water minerals, and you mentioned that there are some concentration of the minerals, heavy minerals, maybe it could be potential the kind of placers. And from this point of view, maybe you should continue to study sediments along the beaches, and this is very, it could be promising from this point of view, as long as in Caspian and in Persian Gulf as well. And another issue about aggregates, I guess you have enough sand in your country, but you can consider this additional source for the sand and gravel in the sea. And for the aggregates, you can consider this type of shallow water deposits for future as a source for the aggregates.
You're right. We plan to work on the placers, but old placers in the shoreline of the last LGM. That might be more concentrated placers. Yeah, it's need to work and more explore deep in the bottom sediment. Yeah, thank you.
Okay, thank you very much for your comments and answers. As far as I know, and according to Zoom chat box, we don't have any other questions for you. So I think we came the end of this session, webinar. So before closing, I would like to thank all speakers who contributed to these deep mineral resources. So I would like to share my screen in order to present your certificate. So, Dr. Behrouz ABTAHI, thank you very much for your contribution to Inter-Islamic Network on Oceanography, giving a lecture on deep sea mineral resources. And I would like to also thank Dr. Hamid Lahiyani for his very nice and excellent presentation. And finally, Professor Dr. Georgi Charkashov, thank you very much for your presentation and contribution to Inter-Islamic Network on Oceanography. I think we, again, this is the final session of this event. I would like to take this opportunity to inform you that Inter-Islamic Network on Oceanography will continue to organize symposium, webinar, workshops for young researchers who are working on marine sciences. So please, in order to learn more about Inter-Islamic Network on Oceanography and future events, please don't forget to visit Inter-Islamic Network on Oceanography webpage and social media accounts. So once again, I also thank to participants who joined us today, and once again, thank you for your time, energy, and dedication. So until we meet again at the next Inter-Islamic Network on Oceanography event, I wish you all good health and success in your work and research. So I would like to ask our speakers if they have any final remarks for this webinar. If not,
can I?
Of course, go ahead, please.
Yes, Miss Dr. Raziyelak, the head of Iranian Institute for Geology, sent some message to our meeting, and I wanted to thank her for her contribution and support. And another thing I wanted to note that Dr. Georgi has a unique experience and is diving with the submersible of Mir. If you know, the Mir is a very famous submersible made in Russia 60 years ago, and for a long time has the record of deep diving in world ocean to a depth of 500 meters, and even now is the progressive scientific submersibles of the world. So Professor Georgi has theoretical knowledge and field knowledge and deep diving. It was very interesting to listen his lecture today, personally for me. Thank you very much.
So thank you very much for your additional comments, Behrouz, for Dr. Georgi Charkashov. So I think we really came the end of this webinar. I would like to thank once again to all participants who joined us today. So for until the next INOC events, I wish you all good health and success in your work and research once again. So
thank you very much.
bye.
Thank you very much. Thank you.